Good morning. I am Dr. Ramya Swetha. Today our topic is force exerted by jet on a curved plate. So before this we know about the some topics. Those are before knowing about these we have to understand those similar topics. So these are the some of the web references which I consider for understanding this particular topic. So in this before going to the topic, these are the things which we have to understand already in previous videos. Those are impact of jets, on which theorem it is going to, on which basis the impact of jets we are going to understand based on which theorem, that is impulse momentum principle, and what are the various conditions which we are facing in these impact of jets for understanding this. So force exerted by jet on vertical plate, whether it is in both situation, that is whether the plate is stationary or vertical, and whenever the plate is moving, so force exerted inclined. So these are all the basics for understanding the force exerted by jet on a curved plate. So in this also, whenever we are having in this also as similar as previous, so the plate is stationary condition and the plate is moving condition, these two which we are going to understand. So in this force exerted by jet on a curved plate, which we are understanding as early conditions, as like early condition, whenever the plate is stationary and whenever the plate is vertical. So in this, and when the plate is stationary and jet strikes at center, so here now we are going to understand that thing. So whenever the flow of jet of water or jet of liquid, whatever is the flow of jet, which velocity v, with the velocity v, with velocity v, with velocity v, it strikes the curved plate whenever the plate is curved, and the curved plate, the jet of water, it strikes at the center. So whenever the jet of water, it strikes at center, and that too the curved plate is in a stationary condition, which is we are going to understand in this particular session. So in this, force exerted by the jet in the direction of the jet, that is always along with the x-axis, and one more thing, that is equal to force based on the previous conditions. The mass per force is equal to along with equal to v1x and v2x. This v1x and v2x are initial and final velocities along the x direction. This is the v1x and v2x. So previously which we consider initial and final velocities. In this, there is no, because of the whenever the plate is like that, after striking the jet of water, the water is also like the parallel to that plate. So that's why we didn't, nothing is going to for the final velocity. But here the plate is in curved condition, curved, and it strikes, and the movement which is not like the curved one, so it moves in both ways, like this and like this. The velocity is going to split like this velocity and this velocity. So before striking, this is the direction, after striking, the direction is going to like this. So that's why here initial and final velocities, that is equal to initial velocity is v, after striking the jet, that is equal to minus v cos theta. So the negative sign indicates velocity at outlet in the opposite direction of the jet water coming from the nozzle. Why we are indicating these negative sign? Why? Because this is the jet of water before striking the curved plate. Once the jet of water touches and strikes the plate, it is going to change its direction like this. So this is going to like this. This is the velocity. So now we understand. So this is the velocity which is not exactly parallel to like this. This is our velocity before striking. This is the velocity before striking, and after striking, this is the one like this. So that's why this is equal to So it makes an angle something, that is theta. This is equal to V cos theta. So this negative, this minus, this negative sign indicates velocity at outlet in the opposite direction of the jet of water. Both are in opposite direction. One, this is the jet of water before strikes direction. Before strikes, and this is the direction after strikes the plate velocity direction. So like that we are going to consider. Now this f of x, now this f of x, like that we are understanding now the force with respect to the x-axis, force exerted by the jet in the direction along the x-axis. So that is equal to rho av v minus, here it is the minus and again minus sign v cos theta. So now f of x is equal to rho av v plus v cos theta. So now we are in these two conditions. The v is the constant one. So now rho a v to v 1 plus cos theta. Now rho a v square 1 plus cos theta is the final force exerted by the jet in the direction of x-axis, in the jet along the x-axis. Now coming to whenever this is the condition for this is the force exerted by the jet on a curved plate, and when the plate is stationary and this strikes at the center condition. In this, similarly, whenever the plate is at the stationary condition. Now move on to the when the plate is moving at jet strikes at the center. Similar situation, but this curved plate is going to move with the velocity that is u. The curved plate with moving velocity u. So here whenever the moving plate is there, we are considering the relative velocity for understanding the force. So now force exerted by the jet in the direction of the z x-axis along the z. So the formula is same. So I'll write here. So the formula is same, that is equal to f of x is equal to mass per second v1 of x minus v2 x. So whenever where v1x is equal to v minus u, why? Because this is the relative velocity between those two when the plate is moving and strikes at the center. And now relative velocity of the jet with respect to the plate, v minus u is the relative velocity which is we are going to consider. Now v1x is equal to v minus u and v2x is equal to minus of minus v minus u cos theta. Already we understand this negative sign indicates the opposite direction of the velocity of the jet after striking the plate. So now f of x is equal to rho a v minus u minus of v minus u cos theta. Finally rho a v minus u square 1 plus cos theta is the force which is considered for the whenever the plate is moving and strikes at the center. So this is the condition. In this, work done per second is equal to f of x into equal to u. So this is the thing which we are considered for the whenever the plate is in both moving and stationary conditions, whenever the plate is comes under curved situation. So now in this till we understand the whenever that is the symmetric condition, the curved plate is at symmetric condition. So it is a symmetric condition. In these situations, coming to next one is unsymmetrical. Coming to the unsymmetrical, so whenever the force exerted by the jet on a stationary curved plate come to the unsymmetrical, jet strikes the curved plate at one end tangentially. That one more condition which we have understand. So here like this. So the jet of water, jet strikes the curved plate at one end. From one end it is going to consider. So here we have to understand the two more things, that those are theta and pi. Whenever the theta angle made the jet x-axis at inlet tip of the plate. At inlet tip of the plate, the angle makes is theta. At outlet of the plate, it considered as pi. So these are the two things which we are going to curved plate, and this is comes under stationary. Force exerted by jet on a stationary curved plate. So jet strikes the curved plate at one end tangentially. The curved plate is unsymmetrical about x-axis, so that the angle made by the tangents at the two ends of the plate will be different. So now that's why we are considering theta and pi. So similarly, force exerted by the jet in the direction of the x, f of x is equal to mass per second v1 minus v2x. Here v1x is equal to cos theta, v2x is equal to pi. Here we are considering v cos pi. Why? Because in this v cos theta, this is the direction of the jet. Generally, we are considering along the x-axis the velocity of the jet, but here the water enters and the water strikes the curved plate like this. So now this is the v1x is equal to, this is, so like this. So that's why this is v sin theta, this is v cos theta. It revolves like this. So that's why this is equal to v1x is equal to, along the x-axis we want, that's why v1x is equal to v cos theta. V cos theta, this is v sin theta, this is the v. So which makes an angle theta. So this is the angle made, that is equal to theta. Similarly, here also it makes an angle pi. This is the v, and both are opposite. So here at curved plate, the water enters at tangentially from inlet. This is v, and this is the v. So now this is the v cos theta, and this is equal to v sin theta. Y-axis, this is equal to x-axis, along the x-axis that is cos. Similarly, here also this is v, it makes an angle with the pi. So along the x-axis, this is equal to pi. So this is equal to v cos pi, and along the direction of pi, v sin pi. Now rho av v cos theta minus, this minus sign indicates the opposite direction. So like this and like this. So both are in opposite direction because of the curved nature of the plate. Whenever the water enters and water strikes, after the striking the water, it leaves at the outlet, the direction is in opposite direction. That's why we consider this negative. Finally, rho av square cos theta plus cos pi is the force under stationary unsymmetrical condition that jet strikes the curved plate at one end tangentially. So similarly, force exert the jet on a moving plate. Here also comes under moving plate. So here what we understand, this velocity of the jet is like this, v1. So here at outlet, that is equal to v2 under unsymmetrical, that to moving curved plate. So this is the curved plate. This is the direction of the that curved plate. So this is here, that is theta, here that is pi at outlet. So the water enters like this. Here we are understanding this one. So like this. So this is equal to relative velocity. So whenever the moving plate is there, we are understanding the, in moving plate condition, we are considering relative velocity. That is VR. That is VR. Here we are understanding these are the parameters. V1 is the absolute velocity of the jet. U1 is the velocity of the vane at inlet. VR1 is the, at inlet we are considering this one. So whenever like this portion at inlet we are considering 1. This is 2 at outlet. At inlet and at outlet. Inlet and outlet. So here V1, VU, V, alpha, theta, VW, VF. These are the various parameters, various components which we are understanding. That VU, VR, alpha, theta, and VW. So these are the parameters. All these 1 at inlet notations. Coming to these alpha and theta, these for the at outlet beta and pi. Remaining all are V2, U2, VR2, VW2. These are the components at outlet. So at outlet, these are the components which we are going to understand. So in this first relative velocity, this is the velocity of the jet which is going to enter. Coming to this all notation, so this is the velocity and this is the moving plate. So this is the relative velocity between those two V1 and U1. This is the moving one, like this, please understand. So like this is the thing. So this is the velocity of the jet, this is the moving plate velocity U, and relative velocity between these two is equal to VR1. For this is the excess portion, this is the flow, and this is the component. From here to here, this complete is the x-axis component, this is the VF1. So it makes an angle between these two is alpha, this is theta. Relative velocity angle, it is theta. So like this we are understanding. Similarly at V2, this is V2 and this is VF2 and this is V2 and this, and velocity, relative velocity, that is equal to movement. Why? Because this is in opposite direction, that movement. So this is like this. So this is the, from this point like this, this is the U2. Relative velocity between is equal to VR2. This is the U2. Moving plate, but U1, U2 are both the same. So coming, this is the VF2 and this is the velocity component. From here to here, VW to horizontal component, this is U2 because of the opposite direction. So this is the outlet at outlet condition, at inlet condition. These are the components which we are going to understand. So V1 is the absolute velocity, U1 is equal to velocity of the vane jet, VR1 is the relative velocity, alpha is the angle by the jet and direction of the motion of the plate at inlet, and it is also known as guide blade angle. And coming to the theta, it's an angle made by the relative velocity. It is an angle made by the relative velocity with the direction of the motion of the vane at the inlet. So this is the blade angle at inlet. This is the guide blade angle. Coming to the components VW1 and VF1, these two are the components of the velocity. So these VW and VF, whether it is there in at inlet or outlet, whether it is whatever it may be, these two are the components of the velocity. So we are understand the components of the velocity. So V in the direction of the motion and perpendicular to the direction of the motion. So whenever along the direction of the motion, we are considering VW as a component. Along the vertical, along the direction, that is equal to VW. So perpendicular direction, that is VF, we are considering. This is nothing but the velocity of the vrille at inlet. So whenever the vane at so the motion respectively. So now VW1 is the velocity of the vrille at inlet, VF1 is the velocity of flow at inlet. So remaining as it is, what are the components? We explain these V, U, VW, VF, alpha, theta, VW and VF. So they are at inlet, we are considering at suffix 1. Similarly, same the whatever the definition and whatever the things are, same components we are considering with the same notation at outlet with suffix 2. That is the difference between these two, V2, U2, VR2. Coming to the alpha, this is beta. Alpha at inlet, beta at outlet, theta at inlet, pi at outlet. And remaining, those are the components. Velocity of the vrille at outlet, velocity of the flow at outlet, those are VW2 and VF2. These are the components which we are going to understand. Based on that, we are understanding the conditions of the unsymmetrical at the velocity of the water, the jet of water, it strikes the curved moving curved plate in unsymmetrical condition, and that too the velocity of the jet strikes at tangentially at one side and it comes outlet from the other end. So those are inlet and outlet condition. These are all the velocity components which we are going to understand in our this particular force exerted by the jet on a moving curved plate under unsymmetrical condition. So these are all the components. Now here, if the van is smooth and having velocity in the direction of the motion at inlet and outlet equal, then we have in this y, because this u1 is equal to u2 is equal to u, because of the direction of the momentum is same, the direction of the move, the velocity of the direction of the curved one is same. So mass of water striking the vane, that is equal to mass is equal to rho a v. So rho a v. Now f of x is equal to, we know based on the momentum impulse of principle, mass per second, that is equal to initial velocity which strike the direction of the motion minus initial velocity minus final velocity. So here initial velocity which strikes the same, so that is equal to VR1, because it is the relative velocity which we consider because of the condition of the given flow. So here the components, these are VR1 is equal to VW1 minus U1. So it is understandable in this diagram clearly. So U1, VW1 now. So VR1 is equal to cos theta is equal to VW1 minus U1. Similarly, component at VR2 at outlet is equal to minus VW2 plus U2y, because this negative sign indicates the opposite directions at inlet and outlet of the impact of the jet. So finally, f of x is equal to, this is the condition. So finally, this is the f of x, force exerted by the jet in the direction of the direction. So this is the work done. So this is the formula. So this is the formula which we will get finally. So how we will get? Based on this, we are u1 is equal to u2 is equal to u, and VR1 cos theta is equal to VW1 minus u1. Similarly, minus VR2 cos pi is equal to minus VW2 plus u2. Here the difference is, it will occur. Why? Because this is the velocity and this is the velocity because of the opposite nature. This is the u2 and this is u2 and this is u2. So like this is the f of 1, this is the only VW2. From here to here we are considering the horizontal component as VW. So this is the final one, and for the work done per second. So this is the end of the force exerted under various conditions for curved plates. So please understand the things. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.